Energy is the ability to do work. You know this. You wake up with a given amount of energy every morning, but that's not what we're talking about. We're not talking about the kind you can chemically get out of a cup from Tim Hortons. 1/2 mass times velocity squared, I shouldn't have said it, equals the kinetic energy of an object. And that's from physical science. That's one of the 3 equations that the state of Ohio thinks you should know in physical science. Ke equals 1/2 mv squared. So how many of you remembered that? How many of you think about that on a regular basis? Good. Awesome. Oh, fantastic. Now, I have a question for you. Kinetic energy is related to both mass and velocity. Which is more important?
Velocity.
Why?
It's squared.
Because it's squared. So there is a video that I used to show in physical science when I taught physical science on the Space Shuttle Challenger explosion. You guys were pretty little when that happened. Wait. Okay, it's a NOVA, PBS NOVA special. It's an hour-long program. It's really good. And they talk about this equation. They mention that equation. So do you know what happened with the Challenger? So remember that this is something that goes up into space and then comes back down through superheated, like tons of friction. Air resistance entering the atmosphere is huge. The thing heats up. So you've got big ceramic tiles on it, and then under that you've got layers of, you know that pink foam insulation they use when they build houses? Basically that stuff. Not exactly that, but it's pretty similar structurally. It's styrofoam insulation under there, because styrofoam is a great insulator. So what was observed when it took off was that a chunk of foam came off one part of the shuttle and hit a wing, hit one of those ceramic tiles. It's a piece of styrofoam. And the engineers actually saw that footage, because they review everything as after the shuttle goes up and everybody's in space and it's all safe and happy. Because being in space is pretty safe. Getting there and getting back are the really, really dangerous parts. So they look at the footage and they see this piece of foam come off. And the engineers at NASA said, it's a piece of styrofoam. It's a piece of styrofoam. And in the PBS NOVA special, one of the engineers who's been reviewing the incident, who did part of the incident report after the disaster, said, it's basic high school physics. I was thrilled when he said this. Ke is 1/2 mass times velocity squared. It doesn't have to weigh a whole lot. It's moving really fast. And that piece of styrofoam hit a tile with enough force to crack it. And cracking a tile means you then have a way for air to get in and tear that apart, and it's disintegrated and then burned up, But it's basic kinetic energy. Things, even if it's really light, if it's moving really fast, it's going to hit with a lot of force. It's got a lot of kinetic energy. Okay, so you are, of course, correct. Velocity is much more critical because it's squared, and I know it says that in your notes, but I'm just going to give you credit for being really clever. So now we get to the work kinetic energy theorem. So we said that work, we rearranged that to get that work is equal to 1/2 mass times the final velocity minus 1/2 mass times the initial velocity squared. If I forgot a squared, I apologize. Well, work net is equal to the change in kinetic energy. Because what we've got there, those should be, okay, I'll fix the typo in a second. That F and I should be subscripted, my apologies. In the top line, work net equals, subscripted. What we're saying is the starting kinetic energy is mass, initial velocity squared divided by 2. That's your initial kinetic energy. Your final kinetic energy is your mass times your final velocity squared divided by 2. That's your change in kinetic energy. So all your net work is equal to is your change in kinetic energy. If you're speeding up or slowing down, the amount of work being done can be determined from that change in kinetic energy. You can use this along with using the force net equals displacement times cosine to solve problems. So this is kind of like where we do sum of forces and net force equals mass times acceleration. So we use those 2 equations and we pair them together. All right, now we'll go ahead and we'll look at the 5B and 5C problems. So we'll start off with page